So we'll get this covered today, but maybe not in this What the heck? I've never seen this mode before. What's happened? Oh, it's doing that thing again. Where's the mute button? Mute. There we go. Right, you got that? Can you see all that? See okay? Yes. Yeah? Oh yeah, you too guys, you never sent me the draft of your essay.
Oh, yeah, I forgot to send it.
Later, send it to me after class.
Yeah.
Okay, continue, you got that? Resistance, resistors, and resistivity. Yeah? Okay, can we start? Yeah. A few things to do. Okay, so I think we mentioned this last week, didn't we? Or did we? Current is the rate of change of charge per unit time. Did we mention that last class? Do you have that definition anywhere?
We had the really long definition.
No, that was the definition of an amp.
No.
Okay, so we'll start by writing this definition down. Current is the rate of change of charge per unit time. Got that? Yeah? Yeah. So, you can actually write it like this, delta Q, delta T, the change in charge per time. Yeah? You got that? What the heck is that? Iced monster, is it?
No,
What
it's
is
just one of the flavors.
Juiced monster. How can you drink that stuff? What flavour is that?
It's like mango and some other stuff. Battery acid.
Yeah, perhaps so. Yeah. Right. Now, the next definition we have is voltage. I think you've heard of this word before, haven't you? Like high voltage. It's a type of energy, potential energy. So, per unit charge, it's measured in joules per coulomb. So 1 volt is a joule per coulomb of charge. So in a way, it's telling us how much work the charge can do. Do you understand? Now, in fact, we call 1 joule per coulomb a volt. So, do you see these things here? These outlets, these sockets. Does anyone know the voltage of these? 220. So that means that 1 coulomb can do 220 joules of work. Do you understand? Yeah. Continue. Now, the next thing is the name of the lesson, which is resistance of an electrical conductor. Is a measure, well, you could perhaps guess from the name even. What do you think it's measuring? It's a measure of what? A sort of opposition to the current. A difficulty to pass the electric current through the conductor. So, conductors are good if their resistance is low. And they're bad if their resistance is high. Now, you know, sometimes you want your conductor to have a high resistance. Can anyone think of an example of maybe when you would want the conductor to have a high resistance? Yeah. Well, one sec, yeah? Yeah, if you actually want to reduce the current, so you want to constrict it. What was your suggestion over here? You're right, you use a high resistance to help protect the ammeter. Yeah. And the other thing is, maybe you want the conductor to have a high resistance because you want it to waste energy producing heat, because you want a heater. You know. So anyways, the unit, does anyone know the unit for resistance? Ohms, yeah. Now, what is the definition of an ohm? So because it's a difficulty, it measures the difficulty of the current. It must do something to the voltage, you know, like if the coulomb has a voltage, it means it has joules of work it can do. But that work must get wasted if it has to try to move through something with a high resistance. So what we say is, you have 1 ohm if you lose a volt per coulomb. You know, so for example, imagine your coulomb can do 10 joules of work, and then it passes through a resistance and it comes out, and now it can only do 9 joules of work. Then we say that there was an ohm of resistance. Now that other form of energy could be anything. For example, when the current goes through this TV and comes out, the resistance wasted, so to speak, the resistance was the light coming off the screen. You know? I suppose what I'm trying to say is, I used to think that resistance always meant something bad, you know, high resistance is bad and low resistance is good, but not really, because the TV has a high resistance because it's doing something you want it to do. You know, when the coulombs come out with less work they can do, it's because they did some work you want them to do. Okay, so I don't know, when I was in school, I always was confused by this because I always thought, oh, resistance was bad and you don't want any resistance. It's not that resistance is bad, it's just resistance is what happens to current when it does some work, and it's either useful work or not useful work. You know, so for example here, is all the work useful for the TV? No, what is wasted? Heat, yeah. So resistance, it sounds like a bad word, but it's not necessarily bad. That's what I'm trying to say. Okay? So, oh sorry, I forgot the end of the definition. So this is obviously per current, so per 1 amp. Is it possible to have 0 resistance? You might recall something I said last week. Is a 0 resistance conductor possible? It is, if you can keep it near 0 Kelvin. In real life, no. But it has been done in the lab. But every conductor has some resistance. Okay, so potential difference, PD, is really just another name for voltage. Now I'm being a little bit loose here, but it'll do for the moment. got that? Yeah? Lynn? Continue? Okay. So the following picture will help explain the relationship between current voltage and resistance. V, I, and or are the letters we use. Now, I searched the internet to try and find a helpful picture to explain the relationship, so this is what I found. When I was Google imaging, I just thought it was too funny not to use. So, this is the resistance. The resistance makes the current harder to pass through, right? And remember, we said the voltage is the work. So, what is the resistance doing? It's wasting the work trying to push the current through. That's what's happening. Don't you like my physics picture? You know him, don't you? He's problem bro. Right? And this is, what's this one? Why you know, isn't it? Yeah? And this one is F-U-U-U-U. You know these guys, don't you? Don't you? Okay, good. So, how do we measure voltage? We measure voltage by using a voltmeter, obviously. And this is what a voltmeter looks like. So, I just want to talk a little bit about this, but the vocabulary is what you need. We measure voltage by using a voltmeter. Now, there's little complication with a voltmeter. Let me explain. So, voltmeters don't work like this. You might think, oh, you know, here's 1 coulomb, and here's 1 coulomb, and here's 1 coulomb, and maybe this one is 10 volts. Remember, 10 volts means 10 joules per coulomb, and it's moving along. So you would think, oh, it'd be nice if the voltmeter could look and see that, oh, there's 10 volts. But that's not how the voltmeter works. Unfortunately, the way the voltmeter works, maybe you have a light here or something, the voltmeter looks at 2 different points in the circuit. Let's say here A and B. And it can't tell you how much voltage is left or how much you had at the beginning. It can only tell you the difference. So, for example, maybe it was 10 joules per coulomb here, and maybe later it could still do 10 joules per coulomb, or 9 joules per coulomb, sorry, because maybe there's another light here or something. But the voltmeter can't tell you that. The voltmeter just tells you between here and here there was 1 joule per coulomb used. In other words, there is a 1 volt between A and B. Okay, so voltmeters only tell you difference in voltage between 2 points. So if you had a voltmeter here and here, and there's nothing happening in between, then it'll say 0 volts, because it can only see the difference between what went in and what came out. Okay, it's a little bit like only being able to tell the difference in the height and not how high you are above the ground. You know, so for example, I know the difference here is 5 centimeters, but I don't know how far each of these are from the ground. Okay. Are we clear with the voltmeter? The next thing, which is a little bit better, is we measure current with an ammeter, and that's much nicer because it can tell you how much current you have going in. It kind of, if you put your ammeter here, then it will tell you, oh, there are 3 amps here, 3 coulombs per second going through. Okay, so you can, I suppose you can think of the ammeter, you know, you can just plug it into the circuit, I can't break this, but you could put the ammeter in here and it could tell you how much current is going through it, how many amps. Remember what 1 amp is? 1 coulomb per second is 1 amp. Remember that? Yeah. So later, Zach will talk about the need to protect the ammeter if the current's too high. But for now, again, the vocabulary is what you need. We measure current using an ammeter. I'm sorry, my stupid Irish accent and pronunciation. So it's obviously ammeter, right? Because A-M-M. But I'm pronouncing it as it's like A''M, which I shouldn't be doing. But what are you going to do? Sue me, I suppose. You probably have noticed sometimes letters get chopped off of words here. Sometimes. Have you seen some pronunciations of Irish names? How do you say this Irish name?
Siobhan.
Good, yeah, you've seen this one.
Seen it before.
Yeah, yeah. It's a bit interesting, the BH in the middle.
Makes a V.
Yeah, yeah. So, things aren't always matched up perfectly.
I think I've got good practice because of playing Crusader Kings 2 on
They have Irish names in it?
the... Yeah, in the Irish...
Great. So you've seen this one then?
No.
Oh. Huh?
Alfie.
Aoife.
Eva.
Aoife, yeah. Right. Okay. Anybody think they might know what you use to measure resistance? Now, give you a hint. We measure voltage using a voltmeter, current using an ammeter. So we measure resistance using a... No. Look at how you're forming the name here. You're using the unit's name. Correct. Ohm meter. Ohm meter, yeah. But we don't usually use these devices because, well, maybe it's different nowadays, but they're very inaccurate, these ohm meters. Sorry, Diego, I'm really, the double M sound is hard for me. I keep wanting to call this an ohm meter instead of an ohm meter. No, screw it, I'm going to call it an ohm meter. Right, so these are very inaccurate. They're very inaccurate. We don't use them. Now, you can get digital ones, and I think they're okay, but I think the syllabus doesn't include this as an equipment item you need to know about for the exam. It's the other two that are more important. But it's not like you're going to forget the name of this anyways, right? Alright, we will not use or study that last device. It's the other two we care about. We'll measure voltage using a voltmeter and we'll measure current using an ammeter. An ammeter requires current to flow through it, like I said here. But a voltmeter measures the voltage between 2 points, like I was talking about earlier. Okay. There is a formula for V, I, and R, and it's a lot like distance, speed, and time. You've got one of these triangles again. So, if I want to know V, how do I calculate that? Yeah, I times R. How do I calculate I? V over R. And how do I calculate R? Yeah, current. So please note this VIR triangle. Got that? Yeah? Continue? Sorry, continue? Yeah. Now, I'll give you a very simple question. We measure the current as being 250 milliamps, and we measure the voltage being 220 volts. My question is, what is the resistance? So the resistance should be the voltage, the potential difference divided by the current. So what is that, please? You can nearly do this in your head.
Do you want it in ohms or milliohms?
Ah, no, give it to me in ohms. Would be suitable. What we got? 880 ohms, isn't it?
This is 80.
Well, it's 220 divided by 0.25. Yeah.
It's milli 10 to the power minus 3.
Yeah. 880. Right?
Yes.
Okay. Easy peasy? Yep. Right. Now, a 6-volt battery is used to power a toy which has resistance of 2 ohms. What is the current flowing through the toy? Okay, so let's do this one together. What's the formula for current?
V over R.
V over R. So in this case, what is it? 3. Fair enough? Okay, next part. If the toy is left on for 1 minute, then how many electrons flow from the battery into and through the toy? So what did we say the current was? 3 amps, which is 3 coulombs per second. And how long is it on for? 60 seconds. So how many coulombs of charge is that? Is 180, right? But that doesn't tell me how many electrons. So how can I work out how many electrons? What do you think? How many electrons? Yeah. So what you need to do next is take the 180 coulombs and divide it by the charge of 1 electron. And in this way we can work out how many electrons were required. Does that make sense? Or should be a big number.
1.125 times 10 to the 1.
Okay, let's write that down. A we said was 3 amps, wasn't it? B is going to be 120 coulombs divided by the charge of 1 electron, which is also in coulombs.
120.
Oh, sorry, 180. Sorry. 180. And so we don't need the units anymore. What do we get?
1.125.
Yeah.
Times 10 to the power 21.
Electrons, which is a lot. Yeah. And finally, if the battery is replaced by 12-volt battery, then how does the current change? Hint, you may assume R is constant, but this is not always the case. And in fact, it's a law that we'll talk about later. So if the R is the same, if the R is still 2, and we have our triangle VIR, and the V is, what do we say? 12. Yeah, so what am I looking for? The I. It's 12 over 2, which is 6 amps now. So the result of, what happened? It doubled.
Yeah.
No, it doubled.
Yes.
Yes, okay. Okay, fine. It's like you put in a bigger battery, 12 volts instead of 6, so you have twice the amount of current. I guess that makes sense. But the R isn't always constant. In real life, if you put in a different battery, you might get a different, or you should get a different resistance.
More internal resistance.
That's it, yeah. But at the moment, we'll just simplify and imagine that the resistance stays constant. Okay, continue. Right, okay, so, actually I should have put this at the front now, because what I did was I put 2 lessons together. Anyways, we're looking next at resistivity. Yeah, Okay, we're good. All electrical devices have a resistance. I mentioned this at the start of the lesson, you remember. So like I said, the TV has a resistance, everything has a resistance. A resistor is an electrical device that has a known fixed amount of resistance, and it's used in experiments and circuits. Normally the work done is heat. So that is, small resistors are really just small heaters. Here's a picture of a 1 ohm resistor. So these little guys are called resistors, and their only job really is to have resistance. And the way they make this resistance is by making heat. But the heat is so small you can't really feel it with your hand. So they're basically fixed resistance in your circuit, and it's sometimes necessary to add these to your circuits. So you were talking about earlier adding it in to reduce the current or the voltage, and you were saying to put it in to protect the ammeter and so on. But with these resistors, they're obviously different. We might wonder what would affect the level of resistance. So if you were to look at this resistor, what things might affect how much resistance there is? Would the length of it affect it? Yeah, possibly. Yeah. So let's talk about it. What things do you think might affect it? So we said the length. What else might affect it? Yep, the diameter would affect it. What else? The temperature might affect it, yeah. Yeah, the material itself, yeah. So we could have the length could affect it, yes. The diameter, you said, yes. The type of material, yes. These could all affect how much resistance we have. In fact, we can put this all together and get a formula. Now, what you have to be careful about is the area is in the denominator. So as it gets fatter, you actually get less resistance. So if you have a small, skinny resistor, you have more resistance. Yeah. The length is on the top, which makes sense. If it's twice as long, it should have twice the resistance. And what do you think the job of this constant is here? It's for the material, yeah. So if the material has a lot of resistance, what do you think this constant is doing? It's bigger value, yeah. L is the length, A is the cross-sectional area. Do you remember this word?
Yes.
And rho is a constant that is different for each material. It's called the resistivity of the material. You got that? So we have to give the definition of that constant. Continue. Resistivity is a measure of how much an electrical conductor stops the flow of electricity through it. Most metals have a low value, and the units, well actually you can look here and you can work out the units. It'll be the ohm meter. Ohm times meter is the unit. There it is there. And it's for measuring how much electrical resistivity there is. So pretty much everything except maybe the second sentence. You don't have to write down the fact that it's usually low for metals. Column never replied. I don't know. You got that? Oops. I need to open up my maps. Okay, you got that? Yep. Lynn? Harry? Yep. Okay. So, for me, I like to give the definitions of insulators and conductors as follows. An insulator will offer an appreciable level of resistance and will often, but not always, have a high level of resistivity. Whereas a conductor, have a guess at how the definition changes, will not offer an appreciable level of resistance and will often, but not always, have a low level of resistivity. Actually, I think we'll get this topic done nicely today. It's not too intense. Got that? You okay? Yeah. Continue? Yes? Right, let's have a look at some values. So the first material we'll have a look at is carbon. So carbon is actually a conductor. I didn't know if you knew that. Did you know that already, or?
Depends what.
The graphite, like in the pencil. Yes, I suppose the carbon that makes up your body fat wouldn't be a conductor.
Oh, like diamond.
But true, yeah, true. Carbon's so strange like that, isn't it? And it's crazy to think that plastic's made out of carbon. Huh? I know. Many things it can do. Okay, so it's a conductor, at least when it's a graphite.
Liquid dye.
Right, copper. Well, copper, conductor or what? Conductor for sure. No, you can see copper is a better conductor than graphite. And graphite's a pretty good conductor to begin with. So copper is actually a really good conductor, it looks like, so far. Yeah.
What is the most conductive material?
It's going to be carbon, but in a very particular structure. I think it's called carbon nanotubes. It's a particular structure of carbon. You can stack the carbon up in a certain way that makes it have, like, practically no resistance. I think, what's it called? Yes, actually, I remember it's some type of carbon. It's like called nanocarbon or something, but it has two interesting features. It's practically a perfect conductor, and it's also a perfect. How can I explain this? A perfect shade of black, meaning any light that falls on it gets absorbed. So it's really weird because you have a little laser pointer and you shine it on this and it disappears. It's so black it perfectly absorbs the light. There's some nice YouTube videos you can look at later. You want to Google something like perfectly black body nano carbon tube or something like this. You can get a video, I'm sure. Okay, next material is nickel. Nickel is also pretty decent as well. Next material is nichrome. I think this is the material that I actually have some of it in the bag.
It's an alloy.
It produces heat quite.
Nickel and chromium.
Yeah. Okay, next material is wood. Now, can you see the huge change between the two? Now, I remember a couple of years ago, I had a student asking me, well, how can a current pass through wood? Because isn't a wood an insulator? Okay, so the point I'm trying to make is, you can pass a current through anything if it's large enough. Okay? And you know this for wood. Can anyone think of an example in real life where a current will pass through wood?
When you have a light.
Lightning. Okay? So, when you're in middle school, you kind of learn this very simple definition of conductor and insulator. Conductor allows a current to pass, and an insulator does not allow a current to pass.
Great difficulty.
Yeah, but that's too simple now as a definition, because you can pass a current through an insulator, okay? You know, that's how they measure your body fat. Your body fat's an insulator, but they measure it by passing a light current through you. Okay? So, I mean, we need to improve our understanding. Wood, you can see how different it is. A huge difference. Huge. Rubber is also very large compared to these conductors. Ginormous. And I'll just do that. So technically speaking, you could make a resistor out of a conductor and vice versa. You know, if you have something like copper, but you want to make it a resistor, then you just need to make the copper have a very small area. Then it becomes a resistor. If you have wood and you want to make it a conductor, then you just make sure it has a very big area, like a tree. Then you can make it like a conductor. Okay. I'm sure in chemistry there's a more formal definition, like a conductor has free electrons or whatever, you know, like this. Okay, continue. So, an electrical heater is really just a piece of nichrome wire with a current running through it. So if the nichrome is 200 centimeters long and 5 millimeters in diameter, then how much resistance is there? Okay, so using the formula R equals rho L over A, calculate the resistance for me, please. And be careful with the units. What you got, Dorian?
0.112.
Okay. I guess I didn't pick realistic numbers, that seems a bit small. Anyways, how do we calculate it? So, R equals rho. What's the rho for nichrome?
1.1.
1.1 times.
25 -6.
So that's the resistivity times L
2.
over area. Pi
0.
or squared. What did you get? 0.112
112.
ohms. Fair enough? Straightforward enough? Yeah? Okay. Not too crazy here. Right, so there's a few minutes left. I'm sure there's probably quite a few questions you can be started with.